Okay, everybody, pressure and atmosphere. And we're going to start off, as with any ILM, we go to the objectives. So I just want to take a second and talk about these objectives here. So on this one, we're going to describe pressure and force, right? That's one of the objectives, and I'm going to spend some time with that. And then we're going to state the 6 principles of hydrostatics. And then we're going to define pressure constants used for calculating pressures. Describe pressure in the effective altitude, which is probably going to be on Wednesday. And perform pressure calculations. We're going to start some of that today. And then perform calculations to convert absolute gauge and mercury pressures. That's almost positively Wednesday as well. Okay, so that's kind of how we're going to break down some of this stuff moving forward. Now, your next couple of pages in your ILM, I completely don't like too much. So I'm going to talk about some stuff right now. So first off, we know from previous assignments, we know what STP is, right? And STP was standard temperature and pressure, and standard temperature is, as you know, 15.5 degrees Celsius or 60 degrees Fahrenheit. We know that to be our standard temperature, and our standard pressure was classified as atmospheric pressure at 14.7 psi or 101 kPa, and that is a metric equivalent, but that is the weight of the atmosphere that is exerted above us at sea level. And there's also a mercury equivalent to these numbers, and that was 29.92 inches of mercury or 760 millimeters of mercury, a metric equivalent of that. So we know that is standard temperature and pressure. And then I want to talk about pressure here. So pressure as it is defined, we're going to define what pressure is. And pressure as a definition is force per unit of area. That's how they define pressure. So pressure is a force per unit of area. And the unit of area that we typically talk about what this is typically square inches. And I'm going to talk about that a little bit more, but I need to, so this is force per unit of area. So I actually should define what they mean by force. And the definition of force is sometimes a push, sometimes it's a pull, and sometimes it's called work. We could define it as, or we express force in pounds. We express force in newtons or kilonewtons, sometimes in kilonewtons. So force is actually the mass, or sometimes called the weight, over the entire area. And we'll talk about force at length and probably on Wednesday. So that's what force is as compared to the pressure. As you can see, this is per unit of area over here. It is the definition of pressure. So force, and if I express force in pounds, and that would be pounds per square inch, or sometimes PSI, pounds per square inch. So that's where that comes from. And we will use pounds per square inch almost always as we talk about it. But of course, pressure can also be expressed in kilopascals. So, and that is just really a metric equivalent to that. Any questions so far? So I'm gonna pull out and start something, and I just want to start off with pressure. So I think we already know if we had a little block, and if we had this block, and this is 1 inch by 1 inch by 1 inch, we know that that's 1 inch cubed. So that's 1 cubic inch. But we know the mass of 1 cubic inch full of water. So if this was full of water, we know that the mass of that is equal to 0.0361 pounds per cubic inch. We know that that cubic inch, if it's full of water, it weighs 0.0361 pounds, and that's per cubic inch. But if we go back up and we look at what the definition of pressure was, it's per square inch. So if I go back into this little box, and if I make a newer one, just so I could see it here. Oh, that's really bad. Let me try that again. So if I had a 1 inch by 1 inch, now the bottom of this box, let me go back, that's the bottom here, is per unit of area. That's an inch squared on the bottom. So this is where we get our pressure gauges, is that we want to know on the bottom of that, per unit of area, per square inch, the mass. So we calculate it in pounds per square inch. So the mass per unit of area. And so 1 square inch, or 1 inch of water, is equal to 0.0361 pounds per square inch per inch of water. So there's that number again. Now the mass of 1 cubic inch of water is 0.0361 pounds, but the pressure per that square inch is the same because we have the 1 square inch on the bottom. So to calculate pressure is by height of the fluid. So if I had 2 inches of water, so if I had 2 blocks on top of here that are 1 inch by 1 inch, I would simply take 2 inches and multiply it by 0.0361 PSI per inch of water. So that would come out to 0.0722 PSI for 2 inches of water. Kind of cool. I'm going to give you some formula on this. Okay, back to the pressure. Here we go, back to my screen. Now everybody can see where we left off. We just talked about just the definitions really of pressure and force. So this is, before I begin, we should probably start talking about the 6 principles. Principles. Boy, I can't spell today. 6 principles of hydrostatic pressure. Now, I'm going to get into doing more calculations with you in a minute, but I think this is super important right here. So these are the 6 principles of hydrostatic pressure. Now, before I begin, hydrostatics. Does anybody know what the term hydro means? Anybody?
Is it water?
Water. Hydro is water, is what we're talking about. And then how about static? Does anybody have an idea what static?
Unmoving or unchanging.
Say that again?
Unmoving or unchanging.
That's right. It's standing still. Kristen, are you taking over my screen here? Thank you. You can highlight stuff as all you want, but so this is still water, okay? Hydrostatic pressure. We are going to talk about water in a piping system, in a vessel, somewhere in a container, but not moving, not circulating. We are talking about water that is still and not moving. Okay, so when we say hydrostatic pressure, it's still water, it's not moving, it's not circulating, it's not going anywhere. All right. So that is the first thing that I want you to know when we're talking about that. Now, number 1 here. Fluid pressure is exerted in all directions. This is one of the principles of hydrostatics. Now, fluid pressure is exerted in all, I don't like this picture in your ILM. It's really tough to understand. This picture in here, they say that mercury is poured in these tubes, and the pressure exerted this way, and air pressure this way, or pressure this way, this way, this way. It's exerted in all directions, okay? Or regardless of the directions, the pressures are all equal. And it's a tough picture to understand. I don't particularly like it. But anyways, fluid pressure is exerted in all directions. That's what you need to know about that. The second principle, it's over here on page 6. The shape of the container. This is number 2 here. The shape of the container does not affect the fluid pressure. Now, this experiment down here, this is Pascal's vase. And although vase B has the greatest volume, as you can see, it has more volume in here. If I had a pressure gauge located right here, it doesn't matter. Or if I had a pressure gauge right here, it doesn't matter. Pressure gauge right here, it doesn't matter. If the height of the fluid is the same for every single container here, then all the pressures are the same. It doesn't matter how big the vessel is. And that's what it's trying to tell us, is that the pressure exerted downwards Doesn't matter how big the container is, it's all about the inches squared at the bottom and the height of the fluid. It's the height of the fluid per unit of area, really. Okay. Now, number 3 principle of hydrostatic pressure is fluid pressure is proportional to depth. So let's get to this picture. Fluid pressure is proportional to depth. So if this is full of water, so if this little diagram here is full of water, at the 1 foot level, we're only going to have this much pressure. So if we have 2 feet of water on top, we're going to have a little more pressure. 3 feet, a little more pressure. 4 feet, a little more pressure. Until we get down here, we have this much pressure being exerted. We have more pressure, is what they're trying to say here. And so, fluid height, this is really important. Height. The height of the fluid, this is how we calculate pressure. Pressure is calculated by the height of the fluid, and we're going to go over some calculations for that. Now, let me just say here, I think we're on number 4, fluid pressure is proportional to density, meaning this is about water. So we're always talking about water here. So when we have a fluid that's heavier than water, for example, mercury is 13.6 times heavier than water, you can see the pressure is going to be different because that fluid density is either heavier or lighter than water. We're going to do all of our calculations today according to water. But if that fluid in there has a different relative density, then the pressure exerted on any gauge will be different. And we will do some calculations according to different densities of fluid or different relative densities of the fluids as well. And then we get over here to number 5. So this is number 5 principle, is horizontal runs do not increase pressure. So what they're saying is gauge A here and gauge B should be exactly the same. So horizontal lines, horizontal is this way, horizontal lines do not affect pressure because pressure is about the height. Pressure is all about the height of the fluid. So this horizontal run does nothing according to pressure. It remains the same as it would at gauge A. And number 6, hydrostatic pressure principle. This is number 6. It doesn't matter on the volume. So these 2 containers that they show in this picture, if I had a pressure gauge at the bottom right here, and if I had a pressure gauge at the bottom right here, they would both read exactly the same. It doesn't matter the volume of the fluid, it matters about the height of the fluid, okay? So no volume means nothing. So I could have 2 pipes side by side. I could have a pipe that's 2 inches diameter. I could have a pipe that's 8 inches diameter. If they're the same height filled with fluid, the pressure is the same at the bottom. The force, however, is different, but we're not talking about that yet. We're only talking about pressure. Any questions so far? So here is our formula triangle for hydrostatic pressure. And the pressure is at the top. So P is equal to the pressure. And the pressure is expressed in pounds per square inch or kilopascals, okay, which is also a metric equivalent to PSI. And what we do is we take the H, where H is equal to the height of the fluid. So this is all about the height of the fluid. And we're talking about water. So we're talking about the height of the water. And then we multiply by D, or sometimes known as a density. Now, it's not the density that we learned in densities in matter. That is a mass per unit of volume. This is going to be a mass. So the density that we're talking about for pressure is a mass per unit of inches squared, or a square inch as in kilopascals, and that is a kilopascal per meter squared on the bottom. So we know already if my height of my fluid is 1 inch, or height of my water is 1 inch high, we would multiply by 0.0361 psi per inch of water. So that's 1 inch of water is equal to 0.0361. So for example, if I had a pipe that was 10 inches in height and it was full of water, what would my pressure gauge read? I simply take 10 inches and multiply it by 0.0361 psi per inch, and my pressure would be 0.361 psi. Not too bad, eh? Pretty easy so far. So what happens if I had a vessel or a pipe? Let me just do this. That was 12 inches in height. So I could say 12 inches multiplied by 0.0361 psi per inch, that would equal 0.433 psi. So this is where we get something called head pressure. Head pressure is a term that we use in our trade, and we talk about head in feet typically, sometimes meters, but most often in feet. So I can say head pressure is 1 foot of water is equal to 0.433 psi. So that is really head pressure as it's defined. So I'm going to rewrite my formula triangle over here. And I told you that the pressure is equal to the height times the density. So if I'm dealing with inches, as you recall, we multiply by 0.0361 psi per inch. So now if I'm talking about feet in height of water, I would simply multiply by 0.433 psi per foot, and this would be head pressure. For example, if I had a piece of, wow, that's not a piece of pipe. If I had a piece of pipe If I had a piece of pipe that was, say, 20 feet tall and it was full of water, what's my pressure at the base? I simply take 20 feet and multiply it by 0.433 PSI per foot. And my pressure on this gauge would be 8.66 PSI. So as you can see, pressure is all about the height of the fluid. Calculating pressure is all about the height of the fluid. Okay. So now there's another number I'm going to give you, and this is the metric equivalent of head pressure, and it is 9. Oh, so hang on. If we're talking about metric equivalent, if I talk about meters, so 1 meter tall, pressure exerted on a column of liquid 1 meter will exert 9.81 kPa per meter. So if I had a building, here's my beautiful building, and I had pressure at the top right here, and if I had this full of water, a pipe bringing water up to the top of the building, and I said that this was 180 meters, it's a pretty big building. What is my pressure gauge at the bottom going to read? I simply take 180 meters tall and I multiply it by 9.81 kPa per meter. And that gives me 1,765.8 kPa on that gauge. So calculating pressures is all about the height of the fluid, all about the height of the fluid. Okay. Now there's another number, and we know standard atmospheric pressure is also measured in inches of mercury. So if I had inches of mercury, I know that mercury is 13.6 times heavier than water. So if I had a column of mercury 1 inch tall, full of mercury, and it's over a square inch base, we know that water is 0.0361 PSI per inch, and mercury is now 13.6 times heavier than water. So if this was mercury in here, what does my pressure gauge read? I simply multiply that by 13.6. So that's going to equal 0.491 PSI per inch mercury. So over here in my formula triangle, I'm going to use the density of 0.491 PSI per inch of mercury. And that's how we calculate inches of mercury. For example, if I had a pipe or column of mercury and that was 18 inches tall and it was full of mercury, what would my pressure gauge read on the bottom? I would simply take 18 inches and multiply it by 0.491 PSI per inch Hg. So this is mercury. And that would equal 8.838 PSI on this gauge. So we're going to go back to the screen and we'll do some calculations according to pressure. For example, if I had a pipe, that's a really terrible piece of pipe. Let me just erase that. I don't know where my good drawing went to. It must have left me somewhere. Okay, so if I had a piece of pipe that was 30 feet tall, and I had a pressure gauge from the floor at 8 feet. I want to know what's on my pressure gauge 8 feet from the bottom of that pipe. So what we have to do is we have to calculate the pressure exerted on that gauge. So we have to figure out the height above that gauge. And I would say that that height above the gauge is 22 feet. So I will take 22 feet and I will multiply it by 0.433 PSI per foot. And this is water. We're only talking about water right now, nothing other, no other substance. So that comes out to 9.5 PSI or pretty close to that. So now I want to tell you one other thing. So if I had a pressure of 1 PSI, I want to know how many feet that 1 PSI will push water. So anytime we're doing a pressure calculation, I kind of want you to remember that formula triangle where the pressure is equal to the height times the density. So if I'm given the pressure, it goes on the top. So I'm given the pressure and I want to know my height. I want to know this right here. So I'll take that out of the formula, put it over here, and I'll take the pressure and I'll divide it by the density. Now the density that I'm talking about is in feet. I want feet. So I'm going to take the 1 PSI and I'm going to divide it by what's my density in feet? 0.433 PSI per foot. And that comes out to 2.31 feet. So the head pressure of 1 PSI will exert water 2.31 feet for every 1 PSI. It's kind of another standard number, that 2.31 feet for 1 PSI. So we'll always use this formula triangle when we're doing any calculations. So for example, if I had a little house here on the prairie and I needed a well, and I'm going to say that my well is 80 feet deep, and I need 50 PSI in my house so I can operate all of my fixtures. So if I had this well that's 80 feet deep, how much pressure does that pump down in the bottom of my well have to produce for me to get 50 PSI in my house? John, Ontario is weird. We're not going to talk about witches yet. Anyways, 80 feet. So first off, I have to calculate the pressure of 80 feet times 0.433 PSI per foot. So this pump has to produce 34.64 PSI to get the water all the way up to this point right here. But I need 50 PSI more in my house. So I'm just simply going to add 50 PSI to that number. So this particular pump that's right here needs to produce 84.64 PSI to get me 50 PSI in my house. UP26 pump is more of a circulator, John. If I'm not mistaken, that's a Grundfos circulator. Okay, let's do another example here. Okay, so say I have 650 kPa at a meter. And the meter is usually at the base of the building. So say if I had a building, really tall building, I don't know how tall. But here's John on the 3rd floor in his window. Okay, so I have 650 kPa coming into this building. I need on the top floor 250 kPa on the top floor. How tall is this building? What is my height here? So what we need to do is we need to know how much pressure I have to lift the water. So first off, in this question, I need 250 at the top. So I have to minus, so I have 650 at the start. I have to minus off 250, minus, not divide. Let me just fix that. So I have to minus, oh, geez, I did it again. I have to minus off 250 minus 250 because I need that at the top. So I only have 400 kPa to push the water upwards. So I got to find out how much that is. So using our formula triangle, where I take the pressure divided by the density will equal my height. So I go 400 kPa divided by 9.81 kPa per meter. So that's going to equal 40.77 meters. So my height here is 40.77 meters. That's how high I can pump that water up. What's that, John?
Nothing. I went on mute for a reason.
Okay. All right, does that make sense? Are we losing anybody yet? Let's do some more examples. How much height let me rephrase that. How much height in inches can I get from 1 PSI? So I want to know the height in inches from 1 PSI. So if I was to use my formula triangle where the pressure, height, density, so 1 PSI then divided by, I want my height in inches. So I need to know that I need to divide that by 0.0361 PSI per inch. And that's going to equal 28 inches of height. So there's kind of another thing. So 28 inches of water will exert a pressure of 1 PSI as well. Let's do another question. I don't think I have that as a picture. Okay, I want everybody to take the next 10 minutes and try to tell me. So the answer is 35.05 PSI. That's how to do that question. So let's look at number 24 here, just above it. What is the pressure at the base of a column of water 16 meters high? Again, always consider your formula triangle where the pressure is equal to the height times the density. So the height is 16 meters. We simply multiply by 9.81 kPa per meter, and we get our pressure. And that pressure is 156.96 kPa. So pretty easy stuff calculating pressures. If we remember the formula triangle and how to get the pressures that are that we're talking about, pay attention to where the gauge is, etc. Okay. So I'm going to pause. Okay, so there's another number that they kind of want us to know, but I don't particularly like this number, but one of the numbers that they want us to know again. So if I was to draw our formula triangle where pressure times the height or density times the height is equal to the pressure, they want us to know in ounces. Oh, let me just erase that. Now they want us to know in ounces per square inch. Now, ounces, and that is pressure in ounces. So they want us to know the pressure in ounces per square inch. But first off, does anybody know how many pounds in an ounce?
There's 16 ounces in a pound.
There we go. So I know that there's 0.0361 pounds per square inch for 1 inch of water. So if I simply take that and multiply by 16 ounces in a pound, this pounds would cancel out. I'm left with 0.578 ounces per inch squared of water. Okay, John, how many grams in an ounce? You know that?
Isn't it like 28?
Yeah, close.
20.
It's close. It's just a bit over 28, but you're right.
How do you know that?
Well, I was born in the 60s, baby. Anyhow, so this is another number that they want us to memorize under here. So here we go. I'm going to give you these densities again. So if we're talking about inches of water, as in my height, we multiply that by 0.0361 psi per inch. That gives me my pressure. We're talking about feet of water. We multiply by 0.433 psi per foot, gives me my pressure. We talk about inches of water again, and if we multiply by 0.578 ounces per inch squared, it gives me my pressure. If we're talking about meters of water, we multiply by 9.81 kPa per meter, gives me my pressure. If we talk about inches of mercury, we multiply by 0.491 psi per inch, and that gives me my pressure. So these are the numbers. These are the numbers that you need to memorize for pressures. Now, you do get this formula triangle. This formula triangle here, you get that on your formula sheet. You get this only. You don't get the numbers. You just get the formula triangle for a TQ, and the formula triangle is in the formula sheet that you get. Now, one other thing that I want to mention to you is that anytime you have a straw or you're trying to suck or pull fluid from a well or a cistern, so say if I had a well that was here and it's full of water and we put a pipe in there and we want to lift the water up into the house. So for a shallow well, we will use a jet pump usually. But how we suck that water up into this pump to go into my house line here, how we do that is that atmospheric pressure is pushing downward. Atmospheric pressure is pushing downward on that fluid. So we're able to take that fluid and actually physically suck it up a pipeline using an impeller that's in there, and it's pulling water, it's sucking it up, but it's atmospheric pressure that's pushing down on this water. So our amount of suction we can get is always according to atmospheric pressure. So if I had atmospheric pressure at sea level at 14 psi, I think that's a standard number that we need to know. And if I wanted to know how many feet of lift I can get from standard pressure, I would simply divide that by 0.433 psi per foot. And I can get about 34 feet of lift from a pump up here, and that would be a perfect vacuum. So that would be perfect lift, and I'm pretty sure I spelled vacuum wrong. So that would be perfect lift. Now I could do it metrically where I could take 9.81 and 101 kPa atmospheric pressure divided by 9.81. That comes out to about 10.4 meters of lift I can get from any kind of suction. So sometimes suction pumps, these jet pumps, they use what's called a Venturi effect. So I'm going to show you this little animation here that I have. Let's see if I can cue this up. So everybody can see my jet pump here. This is a picture of a jet pump. And in this particular jet pump, we have an impeller right here. So there's our impeller. So you can see that. This is called a jet down here. I don't even know why I have this color on here. Let me just clear that off. So this is a jet right in here. So if you can see where my little red pen is, and it goes through this Venturi tube. As you can see, it expands to get bigger. And a couple of things happen with that. So if I was to start this pump, as you can see, this part right here is sucking water from the well, and it's bringing it in and it's pushing it in through this Venturi. This is my impeller that's spinning, and as you can see, it pushes water also through the jet. And we create in this area right here, we're creating a suction zone. So when you have pressure greater than what's in this pipe here, you create this negative pressure zone, and you will literally suck water in there. It would literally suck in there. So you can see we have this Venturi effect, and if you can see the bubbles moving faster, that's actually pulling or lifting or sucking water through this Venturi here to then go to my house line that goes out there. It's kind of cool, isn't it? So let me just show you another way. So the amount, first, let me just say that the amount of lift in a perfect vacuum would be about 34 feet. Quite frankly, the pressure here in Calgary, Alberta is about 12 PSI atmospheric. Okay, so we have less pressure as we come up on higher elevations. There's less pressure to work with. So we're not even going to get close to 34 feet of suction. We're actually going to be much less than that. And in practicality, it's going to be closer to about 20 feet of suction, or 25 feet at sea level. But still, yet again, the higher the elevation to go, the less suction we get out of that. Okay? There's just less suction as you get out of that. So what I'm trying to say is that also at higher elevations, we have less pressure. We talked about that before, I believe, in a very rudimentary way. So let me just go in here and talk about that a little bit more. So my golf ball flies farther. So my little golf ball that has all these dimples on it goes farther at higher elevations. because at higher elevations, there's less atmospheric pressure. So this is at higher elevations. Calgary is about 3,400 feet above sea level. So my golf ball flies farther. Now in Vancouver, where I'm at sea level, my golf ball does not go very far. So my golf ball goes farther in Calgary than it does at sea level. The air is basically heavier. There's more atmospheric pressure on us at sea level. So having said that, things burn hotter at higher elevations, meaning that water boils at lower temperatures. At higher elevations. I was told at some point that water boils at the base camp at Mount Everest at 70 degrees Celsius. So you don't have to go all the way to 100 degrees Celsius to get water to boil. So they're pretty high up in elevation. I can't tell you what the elevation was, but they said that water boils at 70 degrees Celsius. So pretty crazy how this kind of acts on us, this pressure. So we're going to expand a little bit more on that next math class. Okay. So this math class, you are going to be able to start, or if you've already started, entering your marks in for assignment number 7. So assignment number 7 is being released right now. Let me just get that for you. So under the test heading, you will find assignment number 7 called pressures. I want you guys to log into D2L and start your pressure assignment. That's assignment number 7. So you have the next 30 minutes or so to start that. And I will take any questions that you may have as you're starting to work through that, if you need me to answer any questions.